Let's talk extraction. So extractions used all the time in organic chemistry laboratory techniques. One example of extraction in industry is that they used to, well, they still do this, except they do it with water, but they used to decaffeinate coffee beans with dichloromethane, which I'm glad they don't use dichloromethane anymore, but still that's an extraction process. In fact, you do it every morning. If you drink coffee, you're extracting caffeine and all the colored compounds from coffee beans. So that's what we're going to do. Extraction takes advantage of a two-phase system, so we're going to see that we do these experiments in separatory funnels, and you'll put in something like an aqueous layer like water, and maybe ether or dichloromethane is what we're going to be using quite a bit. And dichloromethane and water don't mix because one is nonpolar, or less polar, I should say, than the other one. And so they're going to form a two-phase system. You'll see a distinct layer of dichloromethane that's actually on the bottom of that type of system, whereas most organic solvents float on top because they're less dense than water. So, all right, so we're going to talk about the theory, the procedure, and then later in this video, I'm going to show you the actual techniques. I've filmed some stuff over the summertime. And the principle, the guiding principle that you got to remember, and we've talked about this before, is like dissolves like. So molecules with similar polarity will be miscible with one another. And in this experiment, we're going to be working with caffeine as the first thing we work with. So it's a white solid, and you're going to first measure out 0.17 grams and try to get it to dissolve in water. Now, caffeine is not highly soluble in water, so you may have to spend some time trying to get that 0.17 grams to dissolve in 10 milliliters of water. You might have to use a warm water bath to get it to dissolve. And it does tell you to dissolve it in a centrifuge tube initially, but eventually you're going to transfer it into a separatory funnel, and that's dissolved in water. So the next thing is you're going to transfer it to a separatory funnel. So I've got a picture down here. I'm going to start to sketch out the general procedure of this. So the first step, like I said, is you're going to dissolve caffeine, we'll just call it CAF for short, in water. And once you get it dissolved, it goes right into this separatory funnel. And after that, so that's 10 milliliters of water, by the way. After that, you add 5 milliliters of dichloromethane, and this bottom layer becomes the organic layer. Dichloromethane is one of the few solvents that's going to be on the bottom of a two-phase system like this. Dichloromethane is more dense than water. And then the top layer we call the aqueous layer. And initially the caffeine, like I said, is dissolved in the water, but as soon as we put the stopper in this with the dichloromethane in the water and shake it up a little bit, and we'll talk about that eventually, we're going to see that a lot of the caffeine is going to transfer from the aqueous layer in the organic layer. As it turns out, caffeine is about 5 times more soluble in the dichloromethane layer compared to the water layer. But it's not complete, the transfer, so what we're going to end up doing is after we've shaken this a little bit, what you generally do is you drain out the bottom layer, and the bottom layer goes into a collection flask, and this is going to contain dichloromethane. You're going to want to stop draining the bottom layer right before the water starts coming out. You don't want that water to end up in the dichloromethane layer. Otherwise, you got to get rid of it later. So this is dichloromethane. And at this point, what happens is you still have water inside your separatory funnel, and you're just going to simply add fresh dichloromethane, 5 milliliters again, and then you're going to cap it, you're going to shake it, and once again, any remaining caffeine in the water layer is going to want to transfer from the water to the organic layer, and then you eventually transfer that out. The aqueous layer is still inside, and then you put a fresh shot of dichloromethane in. So the third extraction takes place. By this point, there's very little caffeine left in the organic layer. Most of it's in the organic layer, and you drain that out. Now, the book will tell you to take or keep these 3 dichloromethane layers separate initially, but I say it's okay just to combine them directly. So you're going to use the same flask to collect the bottom layer. But try not to get any water in here. So as you're draining, first of all, don't forget to take the cap out. But secondly, don't let any water get in here because you're going to have to spend some more time getting rid of any water. And you'll know it right away. You'll see bubbles of water in there. Now, all the dichloromethane layers are now combined into one flask, and there's no more water at this point. You can get rid of the aqueous layer. But still what happens is there's a little bit of water still in here. We're going to call it trace amounts. You can't necessarily see the water, but there's always a little bit in there. And generally what happens in extraction at this point is the organic layer, you add to it a drying agent of some kind. I think in our case, we're going to add sodium sulfate. I think that's the drying agent of choice. So anhydrous sodium sulfate is super dry, but as soon as it gets into here, first of all, the sodium sulfate will never dissolve in the dichloromethane, so it's very polar. Dichloromethane is not so polar, and you'll see it as a white solid that just simply collects on the bottom of this flask. It will never dissolve. You don't want it to dissolve. But what it is doing is it's picking up moisture, any moisture that's lingering in the organic layer is picked up by the drying agent, and you'll start to see it clump up. The more it clumps up, the more water was in that flask to begin with. And generally the procedure says to keep adding small scoops of drying agent. So I'm talking about tiny scoops at a time. You swirl the flask, you look for any clumping. Now, when you're done, when the last little scoop of drying agent that you add to this flask does not clump anymore, so it flows freely, then you can know to stop adding drying agent. And don't add too much drying agent, because what happens is you'll have a tough time getting the liquid back out of here when you start to decant, and you'll want to rinse that a couple times. So yeah, there is such a thing as adding too much drying agent. Okay, so once the drying agent is sitting here, sometimes procedures will tell you to let it sit for a couple days, but we're not going to do that. We're just going to let it sit for a couple of minutes, and hopefully all that moisture is being plucked out of the organic layer. And now what you're going to do is carefully decant the liquid. That just means pour off the liquid into a round bottom flask. We're going to use round bottom flask quite a bit in this class. This is a round bottom flask, if you can see this. Well, my pen's not working as usual. There it is right there, round bottom flask. Round bottom flask is used, and you're going to put all the liquid that you can. No solid can go in here. You don't want that. And we're going to start to learn how to use this device, which is called the rotary evaporator. Rotary evaporators are used for removing solvent from mixtures. That's what they do. Okay, so in our case, dichloromethane, we need to get rid of it. Its boiling point, I believe, is in the 50s somewhere. And the way this rotary evaporator works is you hook up that round bottom flask with the liquid inside, and the first thing you do is start to rotate the flask, and what that does is increases the surface area of the dichloromethane so that the rate of evaporation increases. And then this is a water bath. It's a hot water bath, not super hot but warm, and that'll increase the evaporation rate. And then the last thing that's happening all the time is there's a vacuum that's being applied to this whole setup, and the vacuum lowers the atmospheric pressure inside, which also lowers the boiling point of the dichloromethane. So that also helps it evaporate quicker. So those three things combined are what allows us to remove the solvent. And the nice thing about this too is there's a trap that collects all the solvent down here. I'm gonna have to reset my pen, sometimes it quits. There's normally a trap flask down here that collects all the solvent. And this guy right here, this kind of tubey looking thing here is a condenser. So what happens is as those dichloromethane vapors start to volatilize and they travel up here, they hit that cold condenser inside here, and they reliquefy. They drip into this little flask right here. Meanwhile, our compound, our caffeine, stays put here. It's not volatile enough to come up the tube, and so all the solvent is gone. Normally what happens too after rotary evaporation, which just removes the bulk solvent, at this point, what we're going to do is we're going to hook it up to a high vacuum system, and that's just to further dry the caffeine. So we just hook it up to this system. I'll show you how to do that once we get to class, but for about 5 minutes, just to make sure that the drying is complete. And you'll want to pre-weigh your round bottom flask before you transfer the mixture inside here. That way you can get the mass of the caffeine that you recovered later more easily. But anyways, that's the full process. So just in summary, again, really quickly, what we're going to do is we're going to get caffeine to dissolve in water initially, and then we're going to extract it 3 times with dichloromethane, and then the dichloromethane is going to be dried, and then we're going to remove the dichloromethane and then further dry it on the high vacuum, weigh the result. I don't think we're doing a melting point. I think we're just after the mass on this. Caffeine is really tough to get a melting point on, and that's why I guess we're not doing it, so the procedure doesn't call for it. So I really need that mass. How much did you recover after this extraction? Now, there is a pre-lab calculation. Because caffeine is somewhat soluble in water, but it's more soluble in dichloromethane, there is a calculation that you're going to have to do at some point, which has you calculate, well, if we truly start with 0.7 grams in the aqueous layer, by the time we're done with 3 extractions, how much of that caffeine still lingers in the aqueous layer and how much ended up in the dichloromethane layer. It's a pretty tedious calculation. You'll see it described in the textbook as a pre-lab calculation, but you'll also have to dive to the back of the book for the setup. I'm going to briefly talk about the setup now so you can see this, but we want to know, how much caffeine is still left in the aqueous layer. It should be very little by the time we're done with 3 extractions. Okay, so that brings us to partition coefficients. Like I said, caffeine is not perfectly soluble in dichloromethane. And what we have here is the setup for what's known as a partition coefficient. So somebody's already taken the time to measure the partition coefficient for caffeine, and we symbolize this with K. You're probably used to seeing that from Equilibrium. K equals, for caffeine, the concentration in dichloromethane over the concentration in water. And you can see in the bitter end, this is 4.6, which essentially means that it's about 5 times more soluble in dichloromethane than it is in water. What you're going to have to do, though, and this is not the complete calculation, you're going to have to do this several times, is you're going to have to solve for X 3 times. And what X represents is the amount of caffeine after the first extraction that leaves the water layer and ends up in the dichloromethane layer. So you've got to do a lot of algebra to figure out what X is. And not only that, once you have X, then you're going to have to recompute how much is left in the water and plug this back in, and then yet another time, because we are doing a total of 3 total extractions. Now, that is a very tedious calculation. I'll ask for that on a worksheet that I pass out. And just to check your own result, I just created really quickly, this is very crude, but I created this so you can check your result. What I want you to do is to put in your actual mass in this box. So you're going to do the experiment, and you may not have measured exactly 0.17 grams, so maybe you measured 0.169 or whatever. Do this calculation like we talked about, and what you want to know in the bitter end is how much caffeine is left in the aqueous layer. Now, there's 3 extractions, so in the first extraction, which is this column right here, you're going to put in the volume of dichloromethane. It's probably going to be 5 milliliters, and the water is going to be 10 milliliters. In fact, the water is going to be 10 throughout. I don't know why I had 3 separate boxes for this. Water is always 10 milliliters, and then each extraction is 5. So if you didn't use quite 5 milliliters, then fine, change it a little bit. But then you just hit the button. And if you use the numbers that the book talks about, by the time you're done with the calculation, you're going to see that the amount of caffeine in the aqueous layer is very little. It's about 5 milligrams. And the amount of caffeine in the organic layer is 0.165 grams. That's where the bulk of it is. And that makes sense. That's 3 extractions. Okay, so you will have to show your work on that when you see the worksheet. I'm going to pass that out pretty soon. Okay, that's called the partition coefficient. So how do we measure the partition coefficients? For caffeine, somebody's already done it for us. So in part B, you're going to get a chance to measure the partition coefficient for one of 3 compounds. I am going to assign one of those compounds to you. You can check them out in the textbook. You'll see them. One is malonic acid. I think I forget the compounds, but I'm pretty sure one is malonic acid. And what you do is you do an extraction, you do 1 extraction, and you're going to see how that compound that you end up with partitions between 2 solvents, and then you're going to do a calculation. It's a lot easier calculation compared to part A, by the way. You just simply calculate the partition coefficient. Now, that partition coefficient could very well be 0, depending on what you choose. And 0 means that it has virtually no solubility that you can detect in a particular solvent. So that could very well happen depending on what solvents and solutes you end up with. So don't be freaked out if you don't get anything back. That's perfectly normal. Now, you are going to have to share your data with other people in the lab. So we've got 3 compounds, and so a third of the class obviously is going to be doing 1 compound. Another third does another one, another third does another one. So eventually you're going to share that data so that you can know the partition coefficients for all the compounds. All right, so that's part B. Part C, we're going to skip over and just go right to part D. We're not doing part C at all. Part D is probably the most important one. It's called acid-base extraction. And we've sort of gotten hints at how this works in terms of the chemistry earlier in solubility experiment. And this is a common procedure in the organic lab. So the situation is you're going to be given a mixture of a neutral organic compound mixed with an impurity, which is I believe it's benzoic acid, but it's some sort of acidic impurity that's mixed in with it. And your job is to isolate the neutral organic compound, and then eventually you're going to take a melting point of it once it's pure, and you're going to identify it from a list in the textbook. But your job, first of all, is get rid of the benzoic acid, and the acid-base extraction is the perfect situation. The way this works is initially you just dissolve your compound which is a mixture with benzoic acid. This is benzoic acid right here, plus, unknown. The only thing we know about your unknown compound is that it's a neutral compound, so it's not going to do any acid-base chemistry, is what I'm trying to say. Now, the procedure goes something like this. You're going to immediately hit this mixture with sodium hydroxide, and what happens in the chemistry is similar to the solubility experiment. In fact, it's the same thing as the solubility experiment, is you get an acid-base reaction between the acid impurity that forms sodium benzoate and also water. And of course, water ends up in the aqueous layer, duh. But also this one does too. We saw this in the solubility experiment, so this ends up aqueous when before this was organic. But that's how we trick the acid impurity to go out of the organic layer and into the aqueous layer. So that's an extraction technically. We're extracting out the impurity, and the unknown is always dissolved in the organic layer, no matter what. So the unknown does not react with sodium hydroxide, it stays put. And eventually what happens is the unknown, which is still in the organic layer, we dry it first with a drying agent, then we transfer it to a round bottom, and just like we did in part A, and then a rotary evaporator comes next to remove the solvent, and then finally high vacuum drying. After that, in fact there is one more step, after that you're going to do a melting point determination. And like I said before, this allows you to identify the compound. There is a list in the textbook, like I said, so that's how you identify it. So we're mainly after the neutral organic compound. This is sort of a waste product as far as we're concerned. However, the procedure is going to have you do some stuff with the aqueous layer, so don't necessarily throw it out, although in the real world we would throw it out pretty quickly. But don't throw it out right away. There's a couple of little side experiments that you'll do with this, and you'll reacidify this aqueous layer. But that's part D. This is probably arguably the most important part. Try to understand this chemistry, how we're doing this. So again, in the big picture, we are isolating a neutral organic compound away from an acid impurity. It's called an acid-base extraction. So by hitting the impurity with sodium hydroxide, we sort of talk it into going into the aqueous layer, and then we get rid of the aqueous layer eventually. Okay, so at this point, I've covered part A, part B. We're skipping part C, part D. Now what I want to show you, just like in the recrystallization experiment, I'm going to show you the actual techniques, and I'm just going to focus mainly on part A procedure, but part B and part D are exactly the same. So I'm going to show you the rotary evaporators, the separatory funnel, all those kind of stuff. In this experiment, we're going to be looking at extraction. In part A, you're going to be working with caffeine. Here's caffeine in the flesh. You're going to get it from this little jar. The procedure calls for exactly 0.170 grams. It's important that you get near that amount because there's some calculations in the pre-lab that you're going to be doing that you're going to use that value. So really try to dial that in and get all of it into this centrifuge tube. So this is called the centrifuge tube. You're going to pre-mix the caffeine with water and make a solution. Caffeine doesn't dissolve so well in water, so it's going to take you a little bit of time. So I'm going to go ahead and get this started. So 0.17 grams of caffeine, 10 milliliters of water, and I just noticed that this graduate cylinder is broken, so I hope I don't spill all over the place. Okay, so notice that it doesn't dissolve very easily. So I've got I got a small beaker full of hot water. I just got this from the tap. I'm going to let that sit there and heat up a little bit, so that'll hopefully help the dissolving process. In the meantime, I'm going to talk about the glass we're using today. These are called separatory funnels. Most of the drawers have these glass stopcock, which I don't like so much. I'm going to show you how to clean these. The newer ones have the Teflon. The thing about the Teflon before you use the Teflon version is you got to make sure that this is tight. We store these loose so they don't seize up when they're being stored in drawers, but make sure it's reasonably tight. Stopcock turns pretty easily. The stopper's got to be nice and clean for this type of experiment, so I'm going to show you how to clean that. So let's start with this one though. So this is a glass stopcock. Check it, make sure that it rotates smoothly. If it's not rotating smoothly, the way you clean this is you take off this little clip and pull the stopcock out. And I've got a squirt bottle full of acetone. I've got some chem wipes. So what I like to do is just take a chem wipe, squirt some acetone on the chem wipe, Wipe this nice and clean, get all that grease off of there. It's old grease. Try to get as much of the grease inside here off as much as possible. And then we've got a little bit of grease. It's usually stored in the laboratory. And the key thing is, and this is where I mess this up all the time, is I try to put too much grease under the stopcock. So just a small little smear of grease. It goes back in. I'm not going to do this because this one's actually working pretty well. It'd be a shame to do that for this one. But a little bit of grease, kind of smear it around inside, should be ready to go. Don't forget to put the clip back on, otherwise it's going to fall apart on you. I've seen that happen. So the clip is sometimes a little bit of a pain to get back on, but there it goes. Okay, so that's ready to go. A lot of people forget to clean this too. This is essential that you clean this. So again, take a little chem wipe. I'm going to squirt onto the chem wipe, not onto the stopper. Get this nice and clean. If you don't get this clean, the fit's not so good. You're going to have leaks in the separatory funnel. So I'm going to also make sure that I clean the top of this as well. So super clean. That's key. Make sure the stopper fits nice and tight. Okay, these are very expensive, so don't lose these things. The reason why they're expensive is because they're a good fit. We don't want any leaks at the top of this. Believe me, that's a mess. You don't want it. So this one looks pretty good too, but I'm going to clean it just in case. I think this stuff is all clean, but separatory funnels are what we use for extractions. They've got this nice little shape such that by the time we start putting liquids in here, this conical shape like so allows us to see the lines more easily. So what I mean by lines is we're going to typically have two solvents here. A lot of the time we're going to have water as one solvent and some sort of organic solvent as the other solvent. And you're going to see a line of separation. Since the water and the dichloromethane that we're using today don't mix, you're going to see a line. It's nice to have this conical shape to see that pretty easily. Now, most of the time, the aqueous layer, the water layer, is on the bottom, the organic layer is on the top. I'm going to throw a little catch at you right away in that the first part of this experiment uses dichloromethane. That's the one organic solvent that actually floats on the bottom. It's more dense than water, so watch out for that. The water level is going to be on the top, the aqueous layer, and the organic layer is on the bottom. But otherwise, most organic solvents float on top of water. Okay, so these are ready to go. Before you pour anything in here, we've had this happen before. We were laughing about this before we started filming this, but make sure the stopcocks are closed before you start pouring liquids in there. Otherwise, as you can imagine, it's going to pour at the bottom. It's going to be a big mess. Other equipment that's necessary too, these are called funnel stands. These are available in the front part of the laboratory, ring stand, and this is what holds these things. Always use one of those. Now let's check on our caffeine. I haven't really done much to it. Be careful of these caps. A lot of the time they don't work very well. They leak. You don't want leaking. I'm going to go easy on here. It looks like it's okay. All right, so it looks like it's still being a little bit stubborn, so I'm going to cut this video for now. This is our equipment discussion. I'm going to fast forward to the point where I've got this totally dissolved, and we'll pick it up from there. All right, we're about to start our extraction, so I'm going to grab this and show you a few things about this. So eventually we're going to transfer our solution of caffeine and water into the separatory funnel. Again, I can't stress enough, make sure your stopcock is closed before you do that, otherwise you're going to have a nice mess. Make sure your stopper is nice and clean before you do that. So a couple of things. Once I get the caffeine mixture in here, the water and the caffeine, I'm going to add 5 milliliters of dichloromethane to this too. And the key thing is not to do the cucaracha when you're shaking this thing. You don't want to shake it too hard. If you shake it too hard, sometimes you'll get an emulsion. Emulsion is a serious problem, and the layers won't separate very easily. So don't do this, okay? What you want to do is nice, easy, gentle motion. So this is your baby, nice and easy on your baby. You want to get those layers to reasonably be mixed. And frequently what you have to do is burp your baby. We call it burping the baby, where you kind of slightly, always have your finger on this, by the way, too, because sometimes it'll pop off. But burp your baby in that you kind of invert it upwards like this, open up the stopcock, you'll hear a little rush of vapors coming out of here, close it back off, rock it again, frequently vent. Especially when you first start doing the shaking part of it, you're going to want to vent frequently, almost like one shake, and then vent, close it off, shake. It gets a little bit easier as you go. Don't forget to burp your baby, okay? Really essential. Otherwise, I can tell you firsthand that sometimes the stopper, the gases get too pressurized inside there, the stopper comes off, you got a big mess. Be careful of that.
I've got my caffeine mostly dissolved in water, pretty much all the way dissolved. And I'm going to pour the solution into my separatory funnel. Stopcock is closed. I'm going to use the Teflon version of this. And when I pour, I'm also going to make sure I don't spill any on the ground glass joint, because that'll be a problem. When I start to do extraction, it'll start leaking out the top. So notice I almost kind of dunked it in there before I poured. Okay, back out quickly. I'm going to set this down back into the speaker. I'm going to put the stopper on just temporarily for now. Back onto the funnel stand. I've already measured out 5 milliliters of dichloromethane, and I've got it in a grad cylinder. I put a little piece of parafilm. Parafilm is real handy if you're not going to use solvents right away. It just keeps the vapors from coming out into the laboratory. I'm going to warn you about dichloromethane, also known as methylene chloride. Don't get this on your fingers. It's a suspected carcinogen. You don't want that. So be very careful when you work with this. Our nitrile gloves will not protect us from this stuff. It'll go right through those. So I'm going to carefully pour this into my separatory funnel. I'm going to warn you again that dichloromethane is the bottom layer in this experiment. So if you can see this, I'm going to hold this in front of the camera. There's a line of separation that you can just see right there. I'm looking at it from an angle. Hopefully I'm pointing at the right thing here. Water's on top, dichloromethane's on the bottom. And you can see the stopper just pumped out of there. That's the gases that are already building up inside there that did that. So I'm going to make sure that I get my finger on this as soon as possible and start venting frequently or burping our babies as I described it before, okay? All right, so here I go. So I'm going to be careful about this. I'm going to vent right away. Normally I want to vent into the fume hood, so be careful not to vent in your neighbor's face when you do this. Vent again, a little bit of shaking. Vent frequently. It's really important that you vent frequently when you do this. You do not want the stopper coming off. So the reason why the gases build up pressure inside there is just the warmth on my hand is enough to volatilize some of the dichloromethane, and that's why you got to do this frequently. Okay, don't shake this too heavily, especially with dichloromethane. It tends to form an emulsion if you do that too hard. Gets a little bit easier as you go. So what we're doing here is we're doing an extraction. So we're trying to get the caffeine that was originally dissolved in the water to sort of migrate to the dichloromethane. So it's more soluble in the dichloromethane. So that's why it was so hard to get caffeine to dissolve in water. We had to use a hot water bath. But right now, most of the caffeine has now left the aqueous layer and it's now in the dichloromethane layer. We're going to do this a couple more times, but I need to drain out the bottom layer before I kind of proceed to the second extraction. So here's a tiny little beaker, and what I want to make sure is by the time I'm draining the bottom dichloromethane layer out of here is I want to make sure that I don't get any water into this beaker. So I'm going to kind of get close to this at eye level, make sure I don't get any water, the top layer, into this beaker, because water is really hard to remove later. So let's take a look at what we can do. Don't forget to take the stopper out of the top. You won't get it to drain properly if you don't do that. Okay. And that looks good. Okay, so I stopped it before the water came in. I'm going to move this to a different location. I'm not going to show you the whole procedure at this point. The aqueous layer is still in there. The procedure is going to call for a fresh batch of 5 milliliters of dichloromethane that goes back in. You shake it up, you burp your baby, and then you drain out the bottom layer, and you do it a third time, 5 milliliters of fresh dichloromethane back in there, shake it up, vent frequently, drain that. And eventually what's going to happen is we're going to combine the dichloromethane layers, which contains our caffeine, and we're going to dry it. So I'll show you that in just a second. But just make sure you take careful measurements of the caffeine, the water, and the dichloromethane. So this is one of those experiments where we are going to do some calculations. It's important that you take careful measurements of this stuff. So right now our caffeine's in here. I'm going to show you how to remove the solvent under reduced pressure. Okay, before we remove the solvent under reduced pressure for this dichloromethane, this is a combination of the 3 5 milliliter extracts. Most of our caffeine is now in here. There's going to be a tiny amount of caffeine still left in the water, but those pre-lab calculations are going to show you exactly how much is in here, but most of it's in here. Before we can transfer this to the round bottom flask and do rotary evaporation, it's necessary to add this substance. It's called anhydrous sodium sulfate. This is called a drying agent. There's several different drying agents that we can use. This one calls for sodium sulfate. And I'm going to put in a little tiny amount with the end of a spatula. I think the textbook procedure is going to tell you to measure this out, but it's usually not necessary. So I'm just going to guess a little amount into this beaker. And I'm going to check it. I'm going to look at it, swirl around a little bit. And if there's any moisture left in the dichloromethane layer, trace amounts, it's going to clump up with the sodium sulfate. It's going to pick up that moisture, and the solvent is going to be free of that. So if you can get closer here with the camera, let's take a look at this. So it looks like there's a few clumps. So I'm going to add just a tiny amount more, and you're just going to keep adding until you don't see any new clumps. So I just put in a tiny amount. And the amount that I just added looks like it's free flowing, which means that I've added enough. I don't want to add too much drying agent, because if you add too much, the sodium sulfate is picking up that solvent. You're going to get some of the caffeine left behind. Don't do that. And now I'm ready to pour this into my round bottom flask. Usually it's necessary to pre-weigh the round bottom flask. You'll want to do that, so don't forget that step. Clean and dry, weigh it, get the empty mass. And for the most part, most of the time I can get away with just decanting the solution, and the sodium sulfate, the drying agent, just stays behind. But I'm going to keep a careful eye on this, make sure I don't get any of that drying agent in there. Try not to spill on the joints either, because you'll have to clean those and you're going to lose compound. All right, so I'm just transferring all the liquid. Usually you can pretty much do the entire thing without having to use a Pasteur pipette. Just to be safe, I'm going to add a little more dichloromethane to rinse these crystals. I know the textbook procedure doesn't call for this, but I like to do it anyways. I've got a lot of drying agent in here, so this is just clean, fresh dichloromethane that I'm going to add to this drying agent. Just to rinse the crystals. I'm going to add that too. Okay, so I've got all the solution transferred to my round bottom flask. The next step is to do rotary evaporation. That's the technique for removing the solvent environmentally friendly way and quickly. Okay, right now we're about to perform rotary evaporation on a sample. This sample is caffeine that's been dissolved in dichloromethane. Right now Grant's attaching the round bottom flask to the end of the trap, and he's securing it with a Keck clamp, which is the yellow clamp that you should have in your drawer. First step is he angled it into the water bath, and then he's dropping the height of the column into the water. So you want the round bottom to be in the water for sure, but not so low that the lip of the flask is below the water line, because with the vacuum going inside this, it'll suck water into it. So just a little bit into the water. He's making sure that the vacuum release valve is all the way closed off, and then now he's about to turn on the vacuum. So this is the critical step, and so you want to go easy when you turn on the vacuum, because if you don't go too quickly, your sample is going to boil too rapidly and it'll end up in a trap and you'll have to do it over again. It's not the worst thing in the world, but you just want to go easy with the vacuum. So the rotation is also happening too, and you want to start off with that rotation, because the rotation increases the surface area of the solvent inside the flask, and that helps the evaporation rate. But also it's in a hot water bath, so that also enhances the evaporation rate. And the last thing is the vacuum's on, so that reduces the atmospheric pressure inside the flask, and that lowers the boiling point. So right now you can see the condensate is dripping from the coal finger. As the vapors start to travel up the chute, they're going to hit that coal finger, and as soon as they hit the coal finger, which is negative 78 degrees Celsius, it drips back down into the receiving flask or the collection flask, and eventually that flask gets dumped out. So what we're looking for in the case of a solid, which caffeine is a solid, we're looking for no more solvent visible inside the original flask. And so when it's all white solid, that's when we know when this experiment is done. So it should be getting pretty close already. It's a pretty quick process when it comes to caffeine and dichloromethane. And as soon as Grant sees that there's all solid remaining, no liquid whatsoever, he's going to reverse the process and go in reverse order, where he stops the rotation, turns off the vacuum, lifts it out of the water bath. Okay, it looks like there's still a little bit of solvent left to go, and we're still waiting for that moment where there's no more liquid left inside the round bottom flask. Okay, so now the sample is done. We see no more solvent left over in the round bottom flask. Grant is stopping the rotation. We're just going in reverse order. He's angling out of the water bath, raising it up a little bit just so he can get to it easier. He's going to turn off the vacuum at this point. No more vacuum. There's a little red dial that he's releasing now that releases the vacuum. You won't be able to get the round bottom flask off the trap until the vacuum is released. And we're almost set. So you can see now that there's no more liquid left in the round bottom flask. It's all solid. That's what caffeine is. And that's it for rotary evaporation. It's a pretty simple procedure. Now, the only thing that can go wrong in this procedure is your sample, you just go too quickly and your sample violently boils, but that's what the trap is for. So if that happens to you, call me over. I'll show you how to clean out the trap and recover your sample, but it's not the worst thing in the world. Just go easy when it comes to rotary evaporation. So this solvent that we just got done doing was dichloromethane. So that one's pretty straightforward. Sometimes we work with ether, and ether is a little more tricky, so you got to go slow and easy when it comes to the vacuum step. But otherwise, that's the procedure for doing rotary evaporation. Normally after rotary evaporation, we do what's known as high vacuum drying. And the rotary evaporators only remove bulk solvent, so we use this system to remove all traces of the solvent, even if we can't see the solvent at this point. So I have an empty round bottom flask that I'm going to show you how this works in just a second. But of course, you're going to have some sort of solid compound in here, or you're going to have an oil of some kind, and you're going to dry it on this system. The vacuum pump is located down below. Normally, you don't have to mess with this. I've got it off right now because it's way too loud to film it, but it's running, and you'll hear it. We're going to close this cabinet here. This is called a high vacuum manifold, and you see 4 outlets right here. And as soon as I hook up my round bottom flask to one of these 4, there's a really strong vacuum that exists in this system, and eventually the vacuum passes through this cold finger. This is called a Dewar flask, and it's really cold inside there. We keep dry ice and acetone in there, and those vapors are going to hit that cold finger. They're going to condense and fall to the bottom here. But otherwise, when you take a pick amongst these 4 outlets, whenever you can, try to use the trap version. That way, if you have something that splatters pretty easily, the trap will just catch it. We can always clean that. Otherwise, if it's not available, just use one of these. Now again, normally this would be running. I don't have it running right now, but these stopcocks are facing horizontally like so. You're going to see a white tip on each one of these outlets. Just take your pick amongst the outlets, hold it up there for a second. Normally when this is running, you don't need a keck clamp, and you take the white tip and you just face it downwards. You're going to hear a little burst of air rushing out of the flask. That's the vacuum that's kicking in, and then you can just let this round bottom go. Normally we let this sit here for at least 5 minutes, but if you can let it sit longer, do that. So again, what we're doing is we're reducing the atmospheric pressure inside this round bottom flask. That lowers the boiling point of the solvent, and we're trying to remove all traces of the solvent. This is especially important if we're about to do spectroscopy or some other test like melting point. So let that sit there for 5 minutes. When you want to release it, what you do is you do the reverse. You just face the white tip straight up. You're going to hear it release. Catch it, be sure to catch it with your hand, take it off, the next person comes in. But otherwise, hopefully our sample is very dry at this point.